Right. So today, we're going deep, really deep into some
boys.
fascinating mathematics.
Good.
We're diving into dimension theory of noncommutative curves.
Yeah.
Not exactly, light reading,
Right.
but I think the insights here they're really worth it.
Oh, absolutely.
For those of you listening,
Yeah.
we're going to assume that you're already pretty fluent in all this non-computed algebraic geometry.
Yeah.
So we're going to kind of skip, all the introductory stuff,
Right.
and we're going to jump right into the advanced stuff.
Let's get to it.
So are you ready to flex those math muscles?
Absolutely. Let's do it.
Okay, great.
Yeah.
So the abstract of this paper, it kind of jumps right into the thick of things.
Yeah.
It says that this paper, it calculates different dimensions for bounded derived categories of coherent sheaves
Okay.
of orbifold curves. And it says it completes the calculation of these dimensions for non-commutative curves.
Right.
It's kind of like they're saying we've cracked the code.
Yeah. That's a great way to put it. And it's a big accomplishment because understanding those dimensions is so important for being able to classify and really study non-commutative curves.
So to kind of set the stage here a little bit, Reiten and Van, they gave us this really powerful classification.
Right.
They said that non-commutative curves, they're equivalent to either the representation category of a finite acyclic quiver or the category of coherent sheaves on a projective orbifold curve.
Right.
So that's our playground.
Yeah, exactly. In this paper, it takes that foundation and it just goes so much deeper into this really complex world of derived categories and their dimensions.
So they give us this incredibly helpful table.
Yes.
And it's listing, it lists the Roukier dimension, the diagonal dimension, the Serre dimension, and the global dimension.
Right.
Just seeing all these dimensions, I'm feeling a little bit overwhelmed, but like in a good way. Can you give us a quick rundown of what each of these dimensions means and why they matter?
Of course, yeah. So let's start with the Roukier dimension.
Okay.
It basically measures the complexity of a triangulated category.
Oh.
You can think of it as like the number of steps that you need to generate any object in the category, like starting with just a single object and just using cones.
Okay, so a low Roukier dimension, that would mean that the category is relatively simple in terms of how the objects are constructed.
Exactly. Now, the diagonal dimension, that's a little more intricate.
Okay.
It uses this diagonal bimodule to measure the complexity of the relationships between objects within a category.
Okay, so Roukier dimension, that's focused on object construction.
Yes.
And then diagonal dimension is diving into object relationships.
Yeah.
Got it. Okay, what about Serre dimension?
So the Serre dimension, that's connected to the Serre functor of a triangulated category.
Okay.
And it basically shows how twisting by this functor, how it affects the homological properties of objects.
Okay, fascinating. So it's like measuring the impact of a specific operation within the category.
Exactly.
Gotcha. And then finally, we have the global dimension.
Right. The global dimension, that relates to stability conditions on a triangulated category. And it kind of gives you an idea of how the phases of semi-stable objects, how they're spread out.
Okay, so we've got these four distinct ways to grasp the size or the complexity of these categories.
Yes.
Okay, so no wonder this paper is causing such a stir.
Yeah, absolutely. And they don't just define those dimensions, they actually go ahead and compute them for non-commutative curves. Which is pretty remarkable.
Okay, so enough preamble.
Right.
Let's get to the heart of the matter. Let's get to the theorems.
Yeah.
They lay out these three main results.
Yeah.
Theorem A, Theorem B, and Theorem C.
Yes.
And each one's establishing some pretty groundbreaking findings.
Yeah.
So can you give us a little taste of what they say and why they're so important?
Definitely. So Theorem A, that one's all about the Roukier dimension of orbifold curves.
Okay.
And it states that no matter what specific orbifold curve you're looking at, the Roukier dimension, it's always 1.
Wow, that's a strong statement.
It is.
Now, Theorem B, that tackles the diagonal dimension, right?
Yes.
And its relationship with the degree of the canonical bundle of the orbifold curve.
Exactly. And it basically says there's a clear division.
Okay.
The diagonal dimension is 1 if and only if the degree of that canonical bundle, it's negative.
Okay.
Otherwise, it's 2.
Interesting. So a single invariant determines the diagonal dimension.
That's right.
Okay, what about Theorem C?
Theorem C, that takes us into Bridgeland's stability conditions.
Okay.
It proves that they exist for orbifold curves, and it uses that to actually compute the global dimension.
Wow.
And what's amazing is that the central charge of those stability conditions, it factors through the Cenron cohomology of the curve.
Okay, this is getting deep.
It is.
All right, let's roll up our sleeves and let's dive into the paper itself. page by page.
Let's do it.
So they start by reminding us that a non-commutative curve that's defined as an exfinite abelian category with homological dimension 1.
Right, and they really emphasize these key conditions that make this definition work.
Yeah.
Noetherian, smooth, and connected.
Right.
Those are like the bedrock for that really elegant classification of Reiten and Vandenberg.
Okay, now on page 2, they get down to business with the Rouquier dimension.
Yeah.
They give us the formal definition.
Right.
And they explain that it basically captures how quickly you can generate that entire category by starting with a single object and then repeatedly taking cones.
Exactly. And they point out that people have explored this concept in a bunch of other contexts, like with derived categories of coherent sheaves on schemes and derived categories of modules over finite dimensional algebras.
So it's a pretty versatile tool.
It is.
For understanding complexity across different mathematical landscapes.
Yeah.
Okay, so on page 3, we encounter the diagonal dimension.
Yes.
Which is another way to kind of quantify the complexity of a category.
Right.
And they connect it back to the Rouquier dimension.
Right.
They remind us that the diagonal dimension, it's always at least as large as the Rouquier dimension.
Yeah.
But it can be no bigger than twice the dimension of the variety.
Exactly.
So it's like we have this nested hierarchy of complexity measures.
Yeah.
And on that note, they highlight Ollender's work, which proved that for smooth projective curves, the diagonal dimension is 2 if the genus is at least 1.
That's important because it shows how the diagonal dimension, it can actually capture geometric information about the curve.
Okay, so turning to page 4, we encounter the Serre dimension and the global dimension.
Okay.
And as they explain, the Serre dimension, that's tied to the Serre functor of a triangulated category.
Right. And for smooth projective varieties, it just equals the dimension of the variety.
Okay.
It's like the Serre dimension gives you a way to think about the dimension of a geometric object, but in a more categorical way.
So I love how these concepts bridge the gap between algebra and geometry.
Yeah.
Okay, and then they move on to the global dimension.
Right.
Which is defined using the space of stability conditions on a triangulated category.
Right.
And they highlight this really fascinating connection.
Yeah.
For certain categories, the Serre dimension is always less than or equal to the global dimension.
Exactly. And they point out that a lot of times they're actually equal.
Okay.
Which hints at like a deeper relationship that we need to uncover.
It's like these dimensions are all doing this delicate dance.
Yeah.
Influencing each other and constraining each other.
Yeah, it's really cool.
So on page 5, they present this amazing table.
Yes.
It's summarizing the known values of these dimensions for different categories.
Yeah, it's a really great visual aid.
Yeah, it's like a roadmap.
It is.
To help us understand the lay of the land.
Yeah.
And this table makes the paper's mission crystal clear.
Totally.
They want to fill in the missing pieces for orbifold curves.
Exactly, and that's where their big theorems come in. Okay.
Which are stated on pages 5 and 6.
All right, so let's dive into the world of orbifold curves.
Okay.
Starting with section 2.
Right.
They define an orbifold curve as a one-dimensional, non-singular, separated to line-mumfold stack with generically trivial stabilizers.
Yeah, that sounds a little intimidating, but they give you all the background you need.
Okay.
And they highlight how important the coarse moduli space is, which is always a non-singular curve.
Okay.
So this connection to those more familiar curves, it lets them use a lot of familiar tools from algebraic geometry.
Okay.
That's good.
Yeah.
On page 7, they talk about this key property.
Yeah.
Every point with a non-trivial stabilizer group, it has an A-tail neighborhood that looks like the quotient of a smooth curve by a cyclic group.
Right, and that's really crucial because it means we can kind of localize the study of these orbifold curves.
Oh, okay.
You can often reduce questions about the whole curve to questions about these local A-tail neighborhoods, which are a lot easier to work with.
Right, so it's like breaking a complex problem into smaller, more manageable pieces.
Exactly.
Okay, so then they talk about Weil divisors and Cartier divisors on orbifold curves.
Yeah.
And how to define the degree of a divisor.
And here we see something that's a little different from those classical curves.
Okay.
The degree of a point on an orbifold curve, it doesn't have to be an integer. It can be a rational number depending on the order of the stabilizer group at that point.
Okay, so that's how the orbifold structure comes into play.
Exactly. And then they extend this idea of degree to line bundles, and then to the growth NDX group of the curve.
Okay.
They're building up a whole set of tools for working with these objects.
So then on page 8, they delve into some homological properties.
Yes.
Specifically, seroduality.
Right. They remind us that seroduality, it holds for tame, smooth, projective, Deligne-Mumford stacks,
Okay.
which is really important for a lot of their arguments later on.
Okay.
They also prove that the category of coherent sheaves on an orbifold curve, it has homological dimension 1, which is a key ingredient for all their calculations.
Okay, so on page 9, they prove this really helpful decomposition result.
Yes.
Any object in the bounded derived category of coherent sheaves, it's isomorphic to the direct sum of its shifted cohomology objects.
That's great because it means they can work with those objects in the heart of the derived category, which are just coherent sheaves.
Exactly. And then they also prove that any coherent sheaf on an orbifold curve can be decomposed as the direct sum of a torsion sheaf and a locally free sheaf.
They're carefully setting everything up, gathering all these results that are going to be essential for computing those dimensions.
Okay, and then things get even more interesting on pages 9 and 10.
Yes.
Where they introduce slope stability for coherent sheaves on an orbifold curve.
It's like they're taking this idea of stability from vector bundles on curves and they're adapting it for orbifolds.
I see.
Yeah.
And they prove that this definition of stability, it leads to harder Narasimhan filtration.
Right, which are super important for understanding the structure of coherent sheaves. They even show that their definition agrees with the one that uses the modified Hilbert polynomial that Neroni introduced.
Okay, so they're making sure that their definition is compatible with all the previous work.
Exactly.
Okay, great.
Yeah.
So then on page 11, they discuss global generation of sheaves on orbifold curves, introducing the concept of a sheaf being E-generated.
Right.
Where E is a generating sheaf on the curve.
Yeah, it's like a generalization of the usual idea of global generation for sheaves on schemes.
Okay, and they give us some helpful criteria for figuring out when a sheaf is E-generated.
Exactly, which is going to be really important later when they're constructing specific objects for calculating those dimensions.
Right, okay, so then on page 12, we get a glimpse of the orbifold structure at play as they introduce Cheneron cohomology for orbifold curves and define the orbifold Chern character.
Right. It reminds us that we're working with a structure that's richer than ordinary cohomology.
Yeah. Okay.
Yeah, and they emphasize the algebraic Cheneron cohomology, which is going to be essential later when they construct stability conditions.
Okay, so the stage is set.
It is.
We're finally ready to tackle the first major theorem.
Yeah.
Theorem A.
Okay.
Which unveils the secrets of the Rouquier dimension.
Right.
So section 3, that starts on page 12.
Yeah.
And this is where they prove that the Rouquier dimension of a complete tame orbifold curve, it's always 1.
This is a big deal because it means that from the perspective of the Rouquier dimension, these orbifold curves are no more complex than smooth projective curves of genus at least 1.
Okay, so I'm on the edge of my seat.
Yeah.
How do they prove this?
Well, they start by noting that the case where the coarse moduli space of the curve, when that's the projective line, that's already known.
Okay.
So they can focus on that tougher case where the genus of the coarse moduli space is at least 1.
So they're strategically building on what we already know.
Exactly. And to prove the theorem in this case, they need to construct a single object in the derived category that can generate the whole category in just one step.
Okay, that's a tall order.
It is, but they pull it off.
Okay.
They carefully build an object, they call it H.
Okay.
And it's built from a line bundle on the coarse moduli space, a generating sheaf on the orbifold curve, and then all these different twists and duals.
Okay, sounds like a delicate balancing act.
It is, and to prove that this object H is actually a one-step generator, they go through a series of lemmas, starting with lemma 3.3 on page 12.
Okay, so let's break down these lemmas, starting with lemma 3.3.
Okay.
What does that say?
So this lemma, it creates a connection between the vanishing of the first cohomology group of a sheaf and the vanishing of the first cohomology group of the same sheaf, tensored with the dual of the generating sheaf.
Okay, so it's a cohomological condition, and it involves the generating sheaf.
Exactly.
Okay.
And then in lemma 3.4, they extend this result.
Okay.
They show that if a certain cohomology group vanishes, then the sheaf has to be E-generated.
So it's giving us a way to express sheaves in terms of that generating sheaf.
Precisely, and then this leads to lemma 3.5, where they use these results to prove that any torsion sheaf on that orbifold curve, it can be expressed as a quotient of a direct sum of copies of H in its shifts.
Okay, that's a big step.
It is.
That means they've handled all the torsion sheaves.
Right, but to handle those locally free sheaves, they need a couple more tools.
Okay, which is where lemma 3.6 comes in.
Exactly. Lemma 3.6 on page 13. That deals with line bundles on smooth projective curves.
Okay.
And it shows that if the degree of the line bundle is big enough, then it can be generated by just two global sections.
Oh, that's a classic result from algebraic geometry.
It is.
And it's so cool to see how they apply it to these orbifold curves.
Yeah.
Okay, so then comes the real heart of their argument.
Yeah.
Lemma 3.7, or Orlov's main lemma,
Right.
which is also on page 13.
Yeah.
This lemma, it gives us a way to express any vector bundle on the orbifold curve in terms of h, its shifts, and its duals.
It's a really powerful tool.
Okay, so how do they prove it?
They use the harder Narasimhan filtration of the vector bundle to break it down into smaller pieces.
Okay.
And then they cleverly use the previous lemmas to express each piece in terms of h.
So it's like a recursive strategy.
It is.
Breaking the problem down into smaller and smaller pieces until they can solve it.
Exactly. And with that lemma, they can finally finish the proof of Theorem 3.1 on page 14.
Okay, and how do they wrap it all up?
They show that any coherent sheaf on that orbifold curve, it can be expressed as a cone involving h.
Okay.
Which proves that h is a one-step generator.
Right.
And that means the Rouquier dimension has to be 1.
That is impressive.
It is.
They've really tamed the complexity of these orbifold curves.
They have.
At least from the perspective of the Rouquier dimension.
Right.
Okay.
Yeah, and they don't stop there.
Yeah, I can't wait to hear what's next.
I know.
But let's maybe take a break here for now.
Okay, so picking up where we left off, we're going to delve into Theorem B,
Okay.
where we shift our focus to the diagonal dimension.
Okay, so this is where things get even more intriguing, right? Remember, Olander showed us that for smooth projective curves,
Right.
the diagonal dimension depends only on the genus.
Yeah.
It's 1 if the genus is 0 and 2 otherwise.
Exactly.
But what happens when we, go into the world of orbifold curves?
That's a great question, and that's exactly what they tackle in section 4,
Okay.
starting on page 15.
Okay.
And the answer, as they state in Theorem 4.6, is that the diagonal dimension of an orbifold curve, it's 1 if and only if the degree of its canonical bundle is negative.
Okay.
If not, it's 2.
So the orbifold structure, it kind of throws a wrench into the neat picture we had for smooth projective curves.
It does.
The canonical bundles degree, it now plays this really decisive role.
Exactly. And it highlights how the orbifold structure adds this whole new layer of complexity
Right.
that we have to deal with.
Okay, so I'm ready to see how they navigate all this complexity.
Right.
How do they approach the proof of Theorem 4.6?
Well, they use Olander's techniques as a starting point,
Okay.
but they have to make some pretty clever adjustments to handle the orbifold setting.
So what's the first hurdle they need to overcome?
Well, the first thing they need to do is define the structure sheaf of the diagonal
Okay.
for algebraic stacks.
Okay.
For schemes, it's straightforward, but for stacks, the diagonal morphism, it isn't always a monomorphism,
Right.
which creates some subtleties.
Stacks can be tricky,
They can be.
so they need a more refined approach.
Exactly. And they lay the groundwork for this on page 15.
Okay.
And then they prove a key lemma 4.3 on page 16,
Okay.
which extends a result by Ballard and Favero to smooth, tame, and proper stacks that have quasi-projective coarse moduli spaces.
Wow. Okay, what does this lemma tell us?
Okay, so it gives us this really fundamental relationship.
Okay.
It says the Rouquier dimension is always less than or equal to the diagonal dimension,
Okay.
which in turn is less than or equal to twice the dimension of the stack.
Okay, so it gives us these bounds on what the diagonal dimension can be.
Exactly. And for an orbifold curve, that means the diagonal dimension can only be 1 or 2.
So that narrows things down considerably.
It does.
Yeah.
From there, they use a series of reduction steps, just like Olander did for smooth projective curves,
Okay.
to simplify the problem.
Okay, and what's the goal of these reductions?
So the goal is to show that it's enough to consider cases where the structure sheaf of the diagonal is a summand of a cone of a map between objects that have a very specific form,
Okay.
tensor products of vector bundles on the curve.
So they're narrowing down the possibilities to make the problem easier to handle.
Exactly. And with these reductions in place, they dive into the heart of the proof on page 17.
Okay.
And they really carefully analyze the harder Narasimhan filtrations of the vector bundles that are involved.
Filtrations are back.
They are.
These seem to be a recurring theme in their arguments.
They are a powerful tool. And By carefully building specific, short, exact sequences and using a subtle argument that involves slopes and degrees, they show that if the diagonal dimension is 1, then the degree of the canonical bundle has to be negative.
Okay, so they've connected a geometric condition, the diagonal dimension, to a cohomological condition.
Exactly.
The degree of the canonical bundle.
Yeah, they've bridged the gap.
That's pretty impressive.
It is, and that establishes one direction of theorem 4.6.
Okay, so how do they prove the other direction?
For that, they turn to orbifold projective lines. And some really helpful results from Geigel and Lenzing.
Okay, remind me what's so special about orbifold projective lines.
So they explain this on page 18.
Right.
They can be classified based on the degree of their canonical bundle. And what's even cooler is that certain orbifold projective lines are derived equivalent to categories of representations of acyclic quivers.
Okay, so that's a really powerful connection.
It is.
It lets them use the whole theory of quiver representations.
Exactly. And by combining this derived equivalence with some results from Elegen on the diagonal dimension of categories of representations of acyclic quivers, they show that if the degree of the canonical bundle is negative, then the diagonal dimension of the orbifold curve must be 1.
Okay, so it's like they're using a well-mapped territory, like quiver representations, to shed light on the uncharted terrain of orbifold curves.
Exactly, and that completes the proof of theorem 4.6.
Okay.
So now we know exactly when an orbifold curve has diagonal dimension 1.
That's a remarkable achievement.
It is, and I love how they give us concrete examples of orbifold curves with diagonal dimension 1 in corollary 4.7.
Yeah.
It really helps to ground these abstract ideas in something we can actually visualize.
Right.
And then there's corollary 4.8, which links the diagonal dimension to the existence of a tilting bundle with a hereditary endomorphism algebra.
It's amazing, right? They're weaving together all these different parts of math. Geometry, representation theory, homological algebra. To create this beautiful, intricate tapestry.
It's really inspiring to see these connections emerge.
Okay, so we've explored the depths of the Rouquier dimension. We've tackled the intricacies of the diagonal dimension. What uncharted territory lies ahead?
Well, section 5, starting on page 18, invites us to explore the Serre dimension and the global dimension.
Okay, and they start by assuring us that the Serre dimension of an orbifold curve is pretty tame.
Yes.
We can calculate it using the same techniques as we do for smooth projective varieties.
Right, and that leads to corollary 5.2, which says that the Serre dimension of a smooth projective Deligne-Mumford stack, it's just equal to its dimension.
So for an orbifold curve, the Serre dimension is always 1.
Exactly. It's simple and elegant.
Yeah, okay, but as you might expect, the global dimension is a little more elusive.
It is.
So to understand it, they first have to show that the space of stability conditions on the derived category of coherent sheaves on an orbifold curve is not empty.
Right. Stability conditions are a powerful tool for working with derived categories, but they don't always exist.
Right. Okay.
So to tackle this, they focus on stability conditions that factor through the orbifold Chern character, which takes values in the algebraic Chen-Ruan cohomology.
So it's like they're building a bridge between the world of stability conditions and the world of orbifold curves.
Exactly. And to make things a little easier, they limit themselves to orbifold curves over the complex numbers.
Okay, so they're setting the stage for a really focused attack on the global dimension.
Precisely. And on page 19, they present theorem 5.3, which is their main result about stability conditions. This theorem actually constructs a whole family of stability conditions on the derived category of an orbifold curve over the complex numbers.
So they're not just proving that they exist, they're giving us concrete examples.
Exactly.
Okay, that's really impressive.
It is, and what's particularly cool is that these stability conditions satisfy the support property, which is a technical condition that's really important for a lot of applications.
So it's like they're giving us a powerful tool that we can use to explore these categories.
Yeah, and they don't stop there.
Of course not. They've got the global dimension in their sights.
Exactly. And in corollary 5.4, they use these new stability conditions to prove that the global dimension of an orbifold curve over the complex numbers, it's always 1.
It's a beautiful culmination of all their work.
It is.
It shows the deep connections between stability conditions, global dimension, and the geometry of orbifold curves.
Right. It's a testament to how powerful abstract math can be for understanding the structure of objects that seem really complex.
Okay, so we've covered a lot of ground.
We have.
Can you give us a quick recap of the key takeaways from Section 5?
Of course. So we saw that the Serre dimension of an orbifold curve, it's always 1, which comes straight from the result for smooth projective varieties.
Okay.
But the global dimension, that was trickier. To handle that, they had to build these concrete examples of stability conditions on orbifold curves over the complex numbers.
Okay.
And those stability conditions allowed them to prove that the global dimension is always 1.
That's a remarkable achievement.
It is. They've really shed light on the structure of these orbifold curves and their derived categories.
Yeah, they've done something no one else has done before.
Exactly. And their work doesn't end there.
Oh.
They have 2 appendices that give us even more insights and technical details that were super important for their main proofs.
You know, I always feel like the appendices are where the real magic happens.
Me too.
They're like hidden away for the bravest of readers.
I agree.
Okay, so tell me about these appendices.
Okay, so in Appendix A, which starts on page 20, they give us this homological lemma that was key for the proof of theorem 3.1.
Okay, the one about the Rouquier dimension.
Exactly. This lemma gives us a way to write an object in an abelian category as a summand of a cone in the derived category.
So there's a bridge between these 2 different categorical worlds.
Exactly, and it's this bridge that lets them show that their object H is really a one-step generator. Which is the key to understanding the Rouquier dimension.
It's like a secret passageway.
It is.
That leads right to the heart of the proof.
Right. And then in Appendix B, on page 22, they prove a lemma about the stability of the dual of a vector bundle. And this might seem technical, but it's crucial for proving Orlov's main lemma, which was central to that whole Rouquier dimension argument.
Right. It's like a Russian doll of lemmas.
It is.
Each one revealing a deeper layer of the argument.
Yeah, and it's this attention to detail and rigor that makes their work so compelling. They didn't cut any corners in their mission to understand the dimensions of noncommutative curves.
Yeah, okay, well, we've journeyed through 22 pages of dense mathematical arguments. I'm eager to see how they wrap things up.
Me too.
What awaits us on this final stretch?
So on these last few pages, they give us some really illuminating examples that demonstrate how powerful their results are. And they even hint at some potential avenues for future research.
Okay, let's dive in.
Okay, so on page 23, they introduce this pretty fascinating example. The weighted projective line, P1, A1, A2, A3.
Ah, yes, weighted projective lines.
Yeah.
Always a source of intriguing phenomena.
Right.
What do they highlight about them?
Well, they remind us that these weighted projective lines are closely connected to the representation theory of acyclic quivers.
Right, that connection is so elegant.
It is.
How do they use that here?
So they point out that Geigel and Lenzing, they established this beautiful derived equivalence between the category of coherent sheaves on P1, A1, A2, A3, and the derived category of representations of a certain acyclic quiver, which they denote QA1, A2, A3.
So it's like they're showing us that even these these kind of exotic orbifold curves can be understood through quiver representations.
Exactly. And this equivalence lets them use Allegin's results on the diagonal dimension of categories of representations of acyclic quivers.
Ah, so they're connecting different areas of mathematics, right?
Yes.
Using results from one area to understand another.
Precisely. And that leads to a really cool observation. The diagonal dimension of P1, A1, A2, A3. It's one if and only if the quiver QA1, A2, A3 has a very specific form. It's one of those extended Dinkin quivers.
Wow, so the geometry of the weighted projective line is reflected in the structure of the quiver.
Exactly. It's beautiful.
That's really beautiful.
And this connection to quivers actually leads to an even deeper way to characterize orbifold curves with diagonal dimension 1 this time in terms of tilting bundles.
Okay, so tell me about this tilting bundle connection.
Sure. So on page 24, they highlight corollary 4.8, which says that an orbifold curve has diagonal dimension 1. If and only if it has a tilting bundle whose endomorphism algebra is hereditary.
So we've got this geometric concept, the diagonal dimension, linked to the existence of these special bundles with specific algebraic properties.
It's a great example of how geometry and representation theory are intertwined in this work.
Yeah, it's amazing how these different areas of math kind of come together to reveal these deep connections.
It is.
Okay, so we've explored the depths of the diagonal dimension.
Right.
What insights do they offer about the Serre dimension and the global dimension on these last few pages?
Well, as we saw in section 5, the Serre dimension of an orbifold curve is always 1.
Right. That was pretty straightforward.
Yes, it follows directly from the result for smooth projective varieties.
Right. Okay, but the global dimension, that was a bit more of a challenge.
Yeah, it was. To figure it out, they first had to prove that stability conditions exist on the derived category of coherent sheaves on an orbifold curve.
Right, and they did that by focusing on stability conditions that factor through the orbifold Chern character.
Exactly.
Which takes values in the algebraic Chen-Ruan cohomology.
Right, and for simplicity, they just looked at orbifold curves over the complex numbers.
Okay, a strategic simplification that led to some powerful results.
Yeah, so on page 25, they presented theorem 5.3, which actually constructs a family of stability conditions on the derived category of an orbifold curve over the complex numbers.
So they went beyond just proving existence, right?
Right.
They actually gave us concrete examples.
They did, and what's cool is that these stability conditions, they satisfy the support property. Which is really useful for a lot of applications.
So they're giving us this great tool to use for exploring these derived categories.
And with that tool, they were able to prove corollary 5.4. Which states that the global dimension of an orbifold curve over the complex numbers, it's always 1.
That's a fantastic conclusion to their work.
They
really illuminated the dimensional landscape of these non-commutative curves. They revealed all these unexpected connections and all these beautiful results.
It's a really masterful blend of algebra, geometry, and representation theory.
Yeah, this paper's been a real intellectual adventure.
It has.
I'm really left with this sense of awe at the power of abstract mathematics.
Oh, I agree.
To uncover these hidden structures and to connect all these seemingly different ideas.
Yeah, it's a testament to the power and beauty of mathematics.
Yeah, and while this paper has answered a lot of questions, it's also opened up, new avenues for exploration.
For sure.
So there's always more to discover.
Absolutely.
Well, thank you so much for guiding us through this intricate and really rewarding deep dive.
It's been my pleasure.
Your expertise and insights have been invaluable.
Oh, thank you. Your enthusiasm and your insightful questions, they really made this a joy.
And to our listeners, thank you for joining us on this mathematical journey.
Yes, thank you.
We hope you've gained a deeper appreciation for the beauty and the power of the dimension theory of non-commutative curves.
I hope so.
So until next time, keep exploring,
keep
questioning,
keep pushing the boundaries.
And keep pushing the boundaries of mathematical knowledge.
Absolutely.
Welcome back, everybody. Today we're diving into this dimension theory of non-commutative curves. And honestly, I've always found the interplay between algebra and geometry here just remarkable.
It's very interesting for sure. And this paper, it's really quite something. It goes really deep into these different notions of dimension and how they can help us understand, well, these non-commutative curves, specifically these orbifold curves.
Yeah, they go into a bunch of four key dimensions: Rouquier, diagonal, Serre, and global.
Wow.
It's like we've got 4 different, I don't know, lenses or something to look at these objects with.
Yeah, exactly. And what's so interesting is how these dimensions, like how they relate back to more concrete geometric properties of the curves themselves.
Okay, so first things first, what are we talking about? Non-commutative curves. We're defining them here as categories with homological dimension 1, right?
That's right. And Reiten and Vandenberg, they've already kind of set the stage. They classified these into 2 main types: categories of representations of quivers, and then there's categories of coherent sheaves on orbifold curves. So this paper is going to focus on the latter.
Okay, so orbifold curves, they're like regular curves, but with some extras, right?
Yeah. Think of them as curves, but with a few, special points where the geometry gets a bit more, I don't know, interesting or complicated, you could say. And the paper really gets into how these special points, how they actually affect all those dimensions we'll be talking about.
Gotcha. So let's jump into it. Rouquier dimension. What's that all about? What does this dimension even, like, capture?
Well, at its core, Rukia dimension measures how efficiently we can build any object in our category from a single object, this like generating object.
Okay, so it's like, if you had Legos, what's the fewest number of steps to build anything you can imagine?
That's a great analogy. So yeah, a low Rukia dimension means it's, relatively straightforward to build things.
Okay, makes sense. So what about theorem A then? It says that the Rukia dimension of a non-singular and projective and tane orbifold curve is 1. What's, like, the significance of that?
Well, it means these orbifold curves, even if their geometry is complicated, they're actually pretty simple, categorically speaking. We can get any object in the derived category of coherent sheaves, and we only need one step. It really shows just how elegant these objects are.
Interesting. So it's almost like there's just one, like, fundamental building block for the whole structure.
Yeah. And the paper even shows us how to build this block. They call it this object H. And it uses some clever direct sums of certain sheaves. These sheaves are related to line bundles and a generating sheaf on the curve.
Okay, so it's not just, theoretical, it's practical too. So on to the second dimension, diagonal dimension. How is this one, like, defined? How's it different from, Rukia dimension?
It's a bit more, subtle, this one. It looks at how an object in the category relates to itself, but through the lens of tensor products.
Okay, relates to itself through tensor products. What does that even mean? Can you break that down a bit more?
Sure. Imagine you have this object and you want to, I don't know, make a copy of it, a diagonal copy within the category. So diagonal dimension measures, how easily you can build this copy, this diagonal copy, using these tensor products of the object with itself.
So it's about, like, the self-similarity of the object, but through this lens of tensor products.
Exactly. And for smooth projective curves, Allender showed that this dimension, it's determined by the genus. Genus 0, diagonal dimension is 1, genus 1 or higher, it's 2.
Okay, so nice and clean. But it gets more interesting with orbifold curves, right?
Yeah.
Theorem B. It states that the diagonal dimension is 1 if and only if the degree of the canonical bundle is negative. What's the intuition there?
The key is this. A negative degree of the canonical bundle. It's tied to these, they're called tilting bundles, special objects. These bundles, they simplify the category. They make it equivalent to a simpler category where the relationships between the objects are more, straightforward.
Like a secret decoder ring for the categories.
Yeah, exactly. And then there's corollary 4.8. It makes this connection even more clear. It says that diagonal dimension 1, it's basically the same as having this tilting bundle with the specific property. They call it a hereditary endomorphism algebra.
Okay, so the diagonal dimension can tell us if we have these tilting bundles. I like how that ties back into the geometry of the curve.
Yeah.
We've got 2 more dimensions, right? Serre dimension and global dimension.
Yeah. Should we keep going or take a break?
Let's just keep going. What's next?
Okay, so Serre dimension. This one, well, it might seem simple at first, but it's got some, connections to the geometry of these orbifold curves.
Right. Remind me, Serre dimension, what's it all about? Something with the Serre functor, right?
Exactly. The Serre functor, it's like this, mirror that kind of reverses some of the relationships we see in the category. So the Serre dimension, it measures like the complexity of this mirroring.
So it's about how much the category changes when you look at it through this, like, mirror.
Yeah, precisely. And with orbifold curves, corollary 5.2, it gives us a straightforward answer, the Serre dimension. It's always 1.
Always, even if the orbifold curve is super complicated.
Yep, always 1. It comes from a more general result about these smooth projective Deligne-Mumford stacks, which include our orbifold curves. The Serre dimension basically matches the geometric dimension in these cases.
So even though it's defined in this abstract way, it still comes back to the geometry of the curve.
Cool. Okay, last dimension. Global dimension. This one connects to those stability conditions, right?
Right. Global dimension, in a simplified way, you can think of it as measuring the range or the spread of these stability conditions. Like, how diverse can the objects be based on their stability properties?
Okay, so if the global dimension is high, that means there's a lot of variety in how objects are categorized using these stability conditions. What does this paper tell us about the global dimension of, orbifold curves? Well, theorem C. It's got 2 key takeaways. First, for complex orbifold curves, these stability conditions, they exist. And they have a really interesting property. Their central charge, it factors through something called the Chen-Rion cohomology of the orbifold curve.
Chen-Rion cohomology. That sounds intense. What is that, and why is it important here?
Think of it like this. Chen-Ruan cohomology, it helps us see those special points on the orbifold curve where the geometry gets more complex, like a special lens, so we can examine those points in detail.
So it captures the nuances of the geometry.
Yeah.
And the fact that the central charge factors through it, that suggests there's a deep connection between these stability conditions and the geometry itself.
Exactly. Now, the second part of theorem C, if the coarse moduli space of the orbifold curve has genus 1 or more, then its global dimension is 1.
Wait, didn't we say the Serre dimension is always 1 for orbifold curves?
We did, and that's a great point. It means for these orbifold curves, where the coarse moduli space has genus at least 1, the Serre dimension and the global dimension, they're the same, even though we define them completely differently.
So they're both telling us the same thing about the complexity, but from different angles. That's cool.
It is. It hints that there's this deeper connection between these different ideas of dimension. And there's another result. Otani showed that the global dimension of a rational orbifold curve, one with a coarse moduli space of P1, it's also 1.
So no matter what kind of orbifold curve, its global dimension is always 1.
That seems to be the case, and it's pretty remarkable when you think about all the different things global dimension is connected to. The structure of the category, the geometry of the curve, it all kind of comes together.
It's like these dimensions are showing us some fundamental truths about orbifold curves, and they hold true across different settings.
Exactly. And remember, these results, they don't just appear out of thin air. There's a lot of, techniques and insight that go into them. The paper goes into some of the details of the proofs, if you're interested.
Oh, absolutely. I'd love to understand how they get these results. What are some of the key things that go into the proofs?
Well, for theorem A, that's the one about Rouquier dimension, the key is building that special object H that we talked about, the one that acts like a generator for the whole category. They construct it using these direct sums of certain sheaves related to a line bundle on the curve and a generating sheaf.
So it's not just that it exists, they show us how to build it.
Exactly. And then they have a bunch of lemmas showing that any other object in the category, you can get it from H in just one step.
Sounds like a lot of, careful work with sheaves.
Oh, definitely. But that's often the beauty of math, right? It's like a puzzle. You put all the pieces together to get this, coherent picture.
Now, you mentioned that the results about diagonal dimension, they rely on working with this algebraically closed field. Why is that?
It goes back to Olander's original proof for smooth projective curves. He used something called the Harder-Neressimhan filtration, which lets us break down these vector bundles into semi-stable bundles, simpler pieces.
So you're breaking down these complicated things into smaller, easier to work with pieces.
Yeah.
And the filtration, it only works over algebraically closed fields.
Not quite. You can define the filtration over any field, but when the field is algebraically closed, we understand the semi-stable bundles much better. It lets us really analyze that diagonal dimension.
So it's not that it breaks down, it's that our tools aren't as good.
Exactly. And these authors, they adapted Olander's approach to work with these orbifold curves, but they had to keep in mind this restriction to algebraically closed fields.
Okay, makes sense. Back to global dimension and those stability conditions. Corollary 5.4, which says the global dimension of an orbifold curve is 1, the proof looks pretty complicated. What's going on there?
The main idea is to tune these stability conditions so that we can get a specific bound on the global dimension. They show that for any tiny positive number, epsilon, we can make a stability condition where applying the Serre functor basically shifts the phases of these semi-stable objects by 1 plus or minus epsilon.
So you're fine-tuning these stability conditions to control what the Serre functor does, and that gives you a way to put a limit on the global dimension.
Precisely. It's really elegant using the Serre functor and the flexibility of these stability conditions to get this exact result about global dimension.
This is fascinating, but I feel like we're just scratching the surface here. We've looked at these 4 dimensions, but there's got to be so much more to this non-commutative geometry.
Oh, absolutely. This paper is just a glimpse. There are so many unanswered questions and so much to explore. Like, how do these dimensions work in higher dimensional spaces? Are there other dimensions out there, ones we haven't even thought of yet?
Those are great questions. It shows how math is always pushing the boundaries. But before we go too far, maybe we should dig into some of the technical details of what we've talked about so far. Like, I'm curious about lemma 3.7, Orlov's main lemma. It's super important for proving theorem A, but the paper doesn't really go into detail.
Ah, yes, Orlov's main lemma. It's a powerful tool. It gives us a way to build these exact sequences that involve certain types of sheaves, and those are essential for showing that our special object H is a one-step generator.
So it's all about building these exact sequences. Does it use the Harder-Narasimhan filtration again?
It does. Remember that filtration breaks down vector bundles into semi-stable pieces, and those pieces have special properties. If we look at the slopes of these pieces, we can make sure that some cohomology groups vanish.
And that vanishing of cohomology groups, that's what lets you build the exact sequences.
Exactly. It's about carefully working with those sheaves and cohomology groups, but it leads to a strong result. The proof of Lemma 3.7 itself uses a clever trick, with a short exact sequence that connects a line bundle to the trivial bundle.
Interesting. Can you say more about that?
Sure. We start with a short exact sequence using a couple of hyperplanes in projective space. In the sequence, the first and third terms are line bundles, and the middle one is the trivial bundle. When we pull back this sequence to our orbifold curve and tensor it with our vector bundle, we get a new sequence, and this sequence has the properties we need for the lemma.
So you're using the geometry of projective space to make a tool that you can use on the orbifold curve. It's amazing how these abstract things can tell us so much about these categories.
I know, right? And this is just one example of how creative mathematicians can be. We're running out of time, though.
Yeah, maybe we should stop here and continue in the next part.
Sounds good. We still have a lot to talk about, like what these results mean and what might be next for research in this area.
Okay, so we're back, and we've been talking about these non-commutative curves and their dimensions.
Yeah, we've seen some really neat things with these 4 different dimensions and how they give us insight into these orbifold curves.
Totally. But we've been focusing on orbifold curves, which are, one-dimensional. What about higher dimensional spaces? Do these dimensions, make sense beyond curves?
It's a great question, and it's something mathematicians are definitely working on. Non-commutative geometry, it's not just about curves, There are surfaces, threefolds, and so on.
So we can imagine these, higher dimensional versions of orbifold curves. But do our definitions of Rouquier dimension, diagonal dimension, all that, do they still work?
They do, but it gets, a lot more complicated. The definitions are more abstract, and proving things, it takes even more sophisticated techniques.
I can imagine. It's like going from a flat map to a multidimensional maze or something.
Yeah, that's a good way to put it. In higher dimensions, you run into all sorts of new things, new challenges, and we need new tools to tackle them.
So it sounds like there's a whole bunch of open questions, a whole universe of them, in this higher dimensional non-commutative geometry. What are some of the big mysteries that people are trying to solve?
One of the big ones is how these different dimensions relate to each other in these higher dimensions. We saw some interesting connections, like with Serre dimension and global dimension for those orbifold curves, but do they hold more generally? That's the question.
Right, and maybe there are completely new kinds of dimensions in higher dimensions, ones we haven't even thought of.
That could be. The more we learn about non-commutative geometry, the more we realize how much we don't know. It's exciting and humbling, too.
It shows how math is always changing, always pushing forward. It's been a wild ride exploring these non-commutative curves and their dimensions. We've learned so much about how geometry and algebra connect and how these abstract ideas can reveal hidden structures.
I agree. It really shows the beauty and the depth of math and all the possibilities that are still out there.
Well, that's all the time we have for today's deep dive. We hope you've enjoyed this exploration of non-commutative curves and their dimensions.
Keep exploring this fascinating subject. You never know what you might discover.
And until next time, stay curious and keep those questions coming. All right, ready to dive into some dimension theory?
I'm all set. Dimensions are always a fun ride.
This paper by Bhaduri, Goldberg, and Robotis, Dimension Theory of Noncommutative Curves, really digs deep.
Oh yeah, this one goes deep.
They're trying to answer a question that seems almost paradoxical. How do you measure the size of something that isn't geometric in the usual sense?
It's like trying to find the length of a melody, isn't it?
Exactly. You're no stranger to non-commutative algebra, so I know you're going to appreciate this deep dive. We're focusing on 4 key dimensions: Rouquier, diagonal, Serre, and global. Get ready for some surprising connections.
I'm intrigued already. One thing that struck me about this paper is how it bridges the gap between non-commutative algebra and geometry. Specifically, we're zeroing in on orbifold curves.
Right. Those intriguing spaces where you have those fractional points, those stacky points.
Exactly. It's like the best of both worlds, algebra and geometry, all rolled into one.
Now remember, Reiten and Van classified non-commutative curves into representations of quivers in coherent sheaves on orbifold curves.
Oh, absolutely. That's a fundamental result.
Well, in this deep dive, we're focusing on those orbifold curves and what these different dimensions reveal about them. But before we jump into those dimensions, the paper makes a really interesting point in the introduction that I thought was worth highlighting. When we go from an abelian category, like representations of a quiver, to its derived category, we might lose information.
Yeah, it's like viewing the same object through different lenses. You might see different aspects depending on which lens you use.
Can you give an example to illustrate that?
Absolutely. Consider the finite dimensional representations of the Kronecker quiver. As an abelian category, it's not equivalent to the category of coherent sheaves on the projective line.
Right, those are two different beasts.
But when you look at their derived categories, they become equivalent.
Wow, that's wild. So the derived category kind of smooths over differences that exist at the abelian category level.
Precisely. It's something to keep in mind as we explore these dimensions. We're looking at these categories through the lens of the derived category, which can sometimes hide or reveal certain features.
Okay, that's a great point. Now let's get down to business and define what we're actually dealing with here. What are non-commutative curves? How did Reiten and Bergh define them?
They define a non-commutative curve as a k-linear x-finite abelian category with homological dimension 1.
Okay, hold on. Let's unpack that.
Right. It sounds a bit technical, but it's actually quite intuitive.
Let's break it down.
Imagine a category where the objects have a certain fineness property, and the relationships between them, the morphisms, vanish after you shift them a certain number of times.
Okay, so the objects aren't too big or complicated in some sense.
Exactly. And that vanishing of morphisms after shifting is the homological dimension 1 part.
So homological dimension 1 means after shifting objects once, we can't create any new morphisms between them. That seems like a pretty strong constraint.
It is. And this constraint paves the way for their powerful classification theorem, Theorem 1.1. It states that such categories are equivalent to either representations of finite acyclic quivers, which I know you're very familiar with.
Oh yeah, those are a staple in representation theory.
Or, and this is our focus today, coherent sheaves on orbifold curves.
Okay, so we've set the stage with our non-commutative curves, defined and neatly classified. Ready to jump into the first dimension? Rouquier dimension.
Absolutely. Let's get to it.
Intuitively, how can we understand Rouquier dimension? What's the big idea?
Think of Rouquier dimension as a measure of complexity. It tells us how many steps, or more precisely cones, we need to construct any object in the derived category starting from a single generator. The lower the Rouquier dimension, the simpler the category.
So a category with Rouquier dimension 0 would mean we can build every object directly from that generator with no intermediate steps.
You got it. Now, there's this fascinating conjecture by Orlov that relates Rouquier dimension to the geometric dimension of smooth, quasi-projective schemes. And one of the key results in this paper, Theorem A, which is Theorem 3.1, directly addresses this. It states that the Rouquier dimension of a non-singular and projective tame orbifold curve is always 1.
Whoa, hold on. So even with those fractional points that make orbifolds so unique, these curves still act like one-dimensional objects in terms of building things in the derived category.
Isn't that cool? And it aligns perfectly with Orlov's conjecture. Even though orbifold curves have these fractional points, they behave like one-dimensional objects from a homological perspective. This theorem basically confirms that for this particular case.
Okay, I'm starting to see why you were so excited about this paper. So Rouquier dimension gives us a way to quantify how complex it is to build objects in the derived category of an orbifold curve. And for these curves, it's not that complex at all. But now let's move on to diagonal dimension. From what I've read, this one gets a bit more abstract.
Yeah, you're not wrong. Diagonal dimension is defined as the minimal number of steps required to generate the diagonal bimodule of a DG algebra from the external tensor product of perfect modules.
Hold on, I'm feeling a bit lost in the weeds here. Can we unpack that a bit?
Yeah.
What exactly is this diagonal bimodule, and why are we building it on the product of the curve with itself?
Okay, let me try to paint a picture for you. Think of the diagonal bimodule as a sheaf living on the product space of the curve with itself. Imagine you have a square, and the diagonal line connects those opposite corners. That diagonal line sort of relates the two sides of the square, right?
Okay, yeah, I could see that. So the diagonal bimodule is like a sheaf that relates two copies of the curve.
Exactly. And the diagonal dimension tells us how hard it is to build that relating sheaf using sheaves that live on each copy of the curve separately. It's a measure of how entangled the two copies of the curve are in a way.
I like that. It's like asking, how much information do we need to share between the two copies to build this relating sheaf?
Precisely. And Theorem B, which is Theorem 4.6 in the paper, throws a curveball by presenting a surprising dichotomy. It states that an orbifold curve has diagonal dimension 1 if and only if the degree of its canonical bundle is negative. Otherwise, the diagonal dimension is 2.
So the twisting of the curve, which is captured by the degree of its canonical bundle, directly dictates how easily we can build that diagonal sheaf. It's a pretty profound connection.
It really is. It links a purely algebraic concept, the degree of the canonical bundle, to this geometric idea of building a sheaf on a product space.
Okay, my mind is officially blown.
Yeah.
And just to add another layer of complexity, Corollary 4.7 swoops in and tells us that the only orbifold curves with diagonal dimension 1 are very specific families of orbifold projective lines categorized by the orders of their Stacky points.
You're absolutely right. And remember, those families we mentioned earlier, the ones that are derived equivalent to the representation categories of those specific quivers. These are the same families.
Whoa, so it's all coming full circle. We're seeing these deep connections between the representation theory of quivers and the geometry of these orbifold curves. But wait, it gets even more interesting. Corollary 4.8 drops another bombshell by stating that having diagonal dimension 1 is actually equivalent to the existence of a tilting bundle with a hereditary endomorphism algebra.
Right. This is where it gets really cool. This seemingly abstract property about building a diagonal sheaf is directly tied to the existence of a very concrete object, a tilting bundle, with a very special kind of endomorphism algebra.
I'm speechless. It's like we've unearthed the hidden treasure map connecting these different mathematical realms.
It's one of the most striking results of the paper, in my opinion. It underscores the deep connections between these different dimensions and the underlying geometric and algebraic structures of orbifold curves. This unexpected link is what makes this entire exploration so fascinating. That connection between diagonal dimension and tilting bundles is pretty wild, right? Who would have thought those two things would be related?
It's like finding a secret tunnel connecting two seemingly distant parts of a castle. I'm still reeling from that revelation. But we have more dimensions to explore. Let's shift gears now and tackle the next dimension on our list. Serre dimension.
Sounds good to me. On to Serre.
Now, Serre dimension, if I recall correctly, is deeply intertwined with the Serre functor. And the Serre functor, as you know, is a fundamental concept in the world of derived categories.
Yeah.
Can you refresh my memory on how they're connected?
Of course. Remember that for smooth projective varieties, the Serre functor is given by tensoring with the canonical bundle and then shifting by the dimension of the variety. You could think of it as a way to capture this canonical twisting inherent to the category.
So are we essentially trying to quantify how much the category is twisted by its Serre functor? Is that the basic idea?
You got it. In more formal terms, Serre dimension is defined as the categorical entropy of the Serre functor. This entropy measures how quickly the Serre functor expands or contracts objects within the category.
Okay, that makes sense. It's like measuring the stretching or compressing effect of the Serre functor on the objects. But I remember reading in the paper that Serre dimension often aligns nicely with our geometric intuition. Does that hold true for our orbifold curves?
It does. Corollary 5.2 in the paper states that for both smooth projective varieties and, importantly for us, orbifold curves, the Serre dimension actually coincides with the geometric dimension. So for our orbifold curves, the Serre dimension is simply 1.
That's interesting. So unlike diagonal dimension, which had that surprising dichotomy based on the degree of the canonical bundle, Serre dimension seems to provide a more stable notion of dimension. It doesn't seem to be as sensitive to the specific structure of the orbifold curve.
You've made a keen observation. Serre dimension seems to reflect a more inherent property of these categories, regardless of their individual quirks. It's like it's capturing a deeper, more fundamental aspect of their structure.
That's a perfect segue to our final dimension, global dimension. Now this one, if I'm not mistaken, takes us into the realm of stability conditions. Am I right?
You are. It's all about stability conditions. Remember Bridgeland stability conditions. You're already a pro at those.
Oh, you know me, always up for some stability conditions.
Well, these conditions provide a way to break down objects in the derived category into semi-stable pieces, kind of like how we use slope stability for coherent sheaves.
Right. Each semi-stable object gets assigned a phase, which is a real number, categorizing these objects based on their stability level.
Exactly. And the global dimension of a specific stability condition is defined as the maximum difference in phases between any two semi-stable objects that have a non-zero morphism between them. So it essentially measures how spread out those phases are within that particular stability condition.
So it's like asking, given this way of decomposing objects, how far apart can the building blocks be in terms of their phases?
Precisely. Now, to get the global dimension of the entire derived category, we need to take the infimum over all possible Bridgeland stability conditions.
I see. So we're looking for the most compact way to organize the category, where the phases of the semi-stable objects are clustered as close together as possible.
Exactly. And that brings us to Theorem C, which really wraps this whole exploration up nicely. It states that the global dimension of any orbifold curve over the complex numbers is always 1.
Wow, so no matter how exotic or complicated the orbifold curve might be, we can always find a stability condition where the phases of its semi-stable objects are all clustered within a range of 1. That's a pretty powerful statement about the structure of these derived categories.
It is. It suggests a certain uniformity in their structure, even when the underlying orbifold curves themselves can be quite complex.
Now, I remember the paper specifically mentioning using something called Chen-Ruan cohomology to construct these stability conditions on complex orbifold curves. Can you remind me what that is and why it's important here?
Sure. Chen-Ruan cohomology is a refined version of the usual cohomology of an orbifold. It essentially takes those fractional points, those stacky points, into account and provides a richer picture of the orbifold's topology.
So instead of just looking at the coarse moduli space, we're really delving deeper into the stacky structure using Chen-Ruan cohomology.
Exactly. And Theorem 5.3 states that we can actually construct stability conditions where the central charge, the function that determines the phases of objects, factors through this Chen-Ruan cohomology.
So the stacky nature of the orbifold, those fractional points, actually influence how we break down objects in the derived category into those semi-stable pieces. It's like they're leaving their fingerprints on the structure of the derived category.
It's a beautiful illustration of how the geometry and topology of these orbifold curves, including those fractional points, are reflected in the algebraic structure of their derived categories. We've explored these 4 different dimensions, each giving us a different angle on the world of non-commutative curves.
I agree. It's been quite a journey. My head is spinning, but in a good way. We've seen how Rouquier dimension tells us about building objects. Diagonal dimension shows us how intertwined the curve is with itself. Seri dimension captures this inherent canonical twisting. And global dimension reveals a surprising uniformity when we look at stability conditions.
It's amazing how these seemingly disparate concepts are all connected in such profound ways. But maybe a quick recap is in order before we wrap things up and explore the bigger implications of all these dimensions. A recap is definitely a good idea, just to make sure we're all on the same page.
My head is still buzzing a little bit from all these different dimensions. We've covered Rouquier, diagonal, Serre, and global dimensions, each giving us a unique way to look at these non-commutative curves. So what are the key takeaways here? What have we really learned?
Well, I think the most striking thing is how interconnected these dimensions are. Even though they each capture a different aspect of these non-commutative objects, they all relate to each other in these deep and sometimes unexpected ways. They really illuminate the connections between homological algebra, geometry, and representation theory.
Let's break it down one by one just to make sure it all sinks in. We started with Rouquier dimension. It essentially tells us how many steps we need to construct objects from a single generator, right?
Exactly. And that key result, Theorem A, told us that the Rouquier dimension of an orbifold curve is always 1, meaning even with those fractional points, those stacky points, they behave like one-dimensional objects when it comes to their homological properties.
Right, which beautifully aligns with Orlov's conjecture, which relates Rouquier dimension to the geometric dimension of smooth projective schemes. So those fractional points don't really complicate things as much as we might think.
Then we moved on to diagonal dimension, which gives us a totally different perspective. It quantifies how entangled 2 copies of the curve are by looking at how hard it is to build that diagonal sheaf on their product space.
And that's where Theorem B came in, revealing that amazing connection between diagonal dimension and the degree of the canonical bundle. It's wild how the twisting of the curve, which is captured by that canonical bundle, tells us how easy or hard it is to build that diagonal sheaf.
And who could forget Corollary 4.8, which showed us that diagonal dimension 1 is equivalent to having a tilting bundle with a hereditary endomorphism algebra. It connected this abstract property about building a sheaf to the concrete existence of a very special kind of bundle.
Totally. It's like we found a hidden bridge between these seemingly unrelated concepts. But then we shifted gears to Serre dimension, which felt like a more inherent property of the derived category itself, a way to measure the canonical twisting of the category, so to speak. And thankfully, it lined up with our intuition. For orbifold curves, it matched the geometric dimension 1.
You're right. Dimension felt more stable. Like it didn't depend so much on the specific structure of the orbifold curve. It felt more universal, unlike diagonal dimension, which had those specific conditions based on the canonical bundle.
And finally, we landed on global dimension, which brought us into the world of Bridgeland's stability conditions. It gave us a way to measure how spread out the phases of semi-stable objects are in the derived category. And Theorem C showed us that no matter how complicated the orbifold curve might be, there's always a stability condition where the phases are all clustered within a range of 1.
And that construction using Chen-Rowan cohomology to build those stability conditions was really illuminating. It showed us how those fractional points, those stacky points, directly influence how we break down objects in the derived category. It's like those points are leaving their mark on the structure of the derived category.
Absolutely. So we've journeyed through these 4 dimensions, Rouquier, diagonal, Serre, and global, and each one has given us a different angle on the world of non-commutative curves. But what does it all mean? What's the big picture here?
The big picture is that these dimensions aren't just abstract concepts. They provide us with tools, with a framework for understanding these non-commutative objects in a much deeper way. And through them, we see these amazing connections between homological algebra, geometry, and representation theory. They paint a richer, more vibrant picture of the mathematical landscape.
You're right. We've seen how these dimensions offer different perspectives, some aligning with our geometric intuition, and others revealing these unexpected relationships. But this entire deep dive has left me pondering an even bigger question.
Oh, I'm curious. What's on your mind?
We've been focusing on orbifold curves, which are fascinating in their own right. But what about other non-commutative spaces? How might these notions of dimension that we've explored help us understand the wider world of non-commutative algebraic geometry? How do we apply these tools to those more general and often much wilder non-commutative spaces?
That's the million-dollar question, isn't it? And it's a question mathematicians are grappling with right now. How do we take these tools that we've developed and refined on these relatively tame non-commutative curves and use them to navigate the vast and often bewildering world of more general non-commutative spaces? It's a challenge that's definitely worth exploring, and who knows what incredible discoveries await us on that journey.
It's certainly an exciting time to be working in non-commutative algebraic geometry. Well, on that note, I think we've reached the end of our deep dive.
It's been a pleasure exploring these dimensions with you.
Likewise. Until next time. Welcome back, everyone. We're about to take a deep dive into non-commutative curves. And specifically, we're going to unpack the idea of dimension in this pretty abstract world.
Yeah, it's going to be a fun one. We're going to focus on 4 main types of dimensions: Rouquier, diagonal, Serre, and global.
Right. And I think what's really fascinating is that these dimensions, even though they sound super abstract, actually have real quantifiable values when we look at different categories. Like figure 1 in the source material actually shows us this. I'm super curious about diagonal dimension, especially it doesn't always behave the way you think, coming from classical curves.
Yeah, definitely. The way these different dimensions relate to each other is super interesting. They often line up, but sometimes they don't, which kind of hints at some deeper connections we need to explore.
Okay, so let's start with Rouquier dimension. Remind us, what's the basic idea here?
So Rouquier dimension basically tells you how efficiently you can build any object in a triangulated category if you start with just one generator. It's like figuring out the simplest building block and then seeing how many steps it takes to construct the whole thing.
Got it. And one of the key results here is Theorem A, which is Theorem 3.1 in the source material. It says that for orbifold curves, the Rouquier dimension is always 1. This is kind of surprising, right? It seems really simple.
Yeah, it is. It definitely suggests that there's a kind of underlying simplicity to the structure of orbifold curves. The proof basically boils down to constructing a really special generator, which they call H, and then showing that you can get any object from H in just one step. And that step involves forming a cone in the triangulated category.
Okay, so walk me through this construction of H. What makes it so special?
Well, it all comes down to picking H really carefully and making sure it has certain properties, which they list out in Hypotheses 3.2. They basically design H to interact with the derived category of coherent sheaves in a way that lets it generate everything really efficiently. It's a combination of vector bundles and torsion sheaves that, when put together, capture the complexity of the whole derived category.
Interesting. So then lemmas 3.3 through 3.7, these give you the tools to prove that you can express any object as a cone using this H.
Exactly. Those lemmas break down any object in the derived category step by step and show how to build it from H using a sequence of triangles. The authors use the properties of vector bundles and torsion sheaves to carefully figure out how they interact in the derived category. This allows them to prove that H can generate not just individual objects, but the entire category.
Okay, that makes sense. So basically, the proof relies on this clever choice of a generator, H, and then these technical lemmas that show it can generate the whole derived category of coherent sheaves in one step. And that's how they get the result that the Rouquier dimension of orbifold curves is always 1. Seems like a powerful approach. Do you think this could be used to study the Rouquier dimension of other types of non-commutative spaces?
That's a really good question. I mean, the way they built H relies heavily on the specific characteristics of orbifold curves, but the general strategy, finding a strong generator and seeing what it can reach in the derived category, could definitely be adapted to other situations. It would be really interesting to see if you get similar low-dimensional results in other categories, or if you need more complex generators.
All right, let's shift gears and talk about diagonal dimension. You mentioned earlier that it can be a bit unpredictable. What do you mean by that?
Well, with smooth curves, diagonal dimension is pretty straightforward. Olander's result, which is theorem 4.1, says it's 1 for genus 0 and 2 for genus 1 or higher, which makes sense geometrically. But with orbifold curves, things get a little more tricky.
Okay, so what's the catch?
So theorem B, which is theorem 4.6 in the paper, shows that the diagonal dimension of an orbifold curve depends on the degree of its canonical bundle. If that degree is negative, you surprisingly get a diagonal dimension of 1, no matter what the genus is. But if the degree is not negative, then the dimension is 2, like we'd expect from the smooth case.
Interesting. So it's like having a negative degree somehow simplifies the diagonal, right?
You could definitely interpret it that way. It seems like orbifold curves with a negative canonical bundle degree have some special features that simplify things when you look at them through the lens of diagonal dimension.
I see. And how does this relate back to the actual definition of diagonal dimension, which is about the complexity of the diagonal object within the category?
Right, so the diagonal object is kind of like a representation of the self-intersection of the curve inside its product with itself. Diagonal dimension basically measures how efficiently you can resolve this diagonal object using other objects from the category. So when you have a negative canonical degree, it seems like the diagonal object has a simpler resolution, which leads to the lower dimension.
Okay, that makes sense. So now I'm curious. Does this unexpected behavior of diagonal dimension tell us anything deeper about the structure of orbifold curves?
It definitely suggests there's more to discover. And corollary 4.8 actually gives us some clues. It connects diagonal dimension to the existence of tilting bundles and the properties of their endomorphism algebras.
Hold on, let's break that down. What are tilting bundles and why do they matter here?
Tilting bundles are these special objects in the derived category that, in a way, tilt the category in a specific direction. They give us a way to break down objects and understand the structure of the category in a simpler way. Corollary 4.8 says that having a diagonal dimension of 1 is the same as having a tilting bundle where the endomorphism algebra is hereditary.
And hereditary algebras are nice to work with, right? They have some good properties.
Exactly. They're much easier to handle. So this suggests that orbifold curves with a negative canonical bundle degree, which have diagonal dimension 1, might have a kind of tameness or simplicity in their derived categories that's missing in those with higher dimensions.
So diagonal dimension isn't just some abstract measure. It actually reflects something deeper about the structure of these categories. It's fascinating how these abstract concepts can have such concrete implications.
Yeah, it really shows you the power of abstraction in math. So we've dug into Rouquier and diagonal dimensions. Are you ready to move on to Serre and global dimensions?
Absolutely. But let's pause here for a moment and let all of that sink in. It's already a lot to process, and these initial findings are super interesting.
Okay, so let's jump into Serre dimension. This one's closely tied to the Serre functor, which is super important for duality theory in derived categories.
Right, the Serre functor is kind of like a mirror, reflecting objects and showing us symmetries and relationships. So how does Serre dimension capture this reflection?
Basically, Serre dimension measures how much the Serre functor changes the complexity of objects in the derived category. It's like gauging how much the reflection twists things. And for orbifold curves, the cool thing is that the Serre dimension is always 1, according to corollary 5.2.
So even in this really abstract world, Serre dimension brings us back to something familiar, the dimension of the curve itself.
Exactly. Now let's switch gears to the global dimension. This one's all about stability conditions, which give us a way to organize the objects in our category.
So stability conditions are like a map with different regions, and each region has objects with specific stability properties.
Yeah, that's a good way to think about it. Global dimension basically measures how spread out these stability regions are. It tells you how far apart objects with different stability properties can be on this map.
Got it. And what about orbifold curves? What's their global dimension?
Well, figuring out global dimension can be tough because you have to really understand the space of stability conditions. But for orbifold curves, we actually have a clear answer. Corollary 5.4 says that the global dimension is always 1.
Wow, another dimension that matches our geometric intuition. It's really interesting how these different ideas about dimension, each with its own angle, come together so nicely for orbifold curves. Can you tell us a bit more about how they prove this?
Sure. The key is Theorem 5.3, which shows that there are good stability conditions for orbifold curves. They construct these special stability conditions that work well with the Serre functor.
What do you mean by work well?
It means that when you apply the Serre functor to an object, its position in the stability space only shifts by a controlled amount. This control is really important for getting that global dimension bound of 1. If the Serre functor messed up an object's stability in a big way, the global dimension could be much higher.
So these special stability conditions keep the Serre functor from spreading objects too far apart in the stability space, which keeps the global dimension at 1.
Precisely. And the proof uses this thing called the Chen-Ruan cohomology of the orbifold curve. This cohomology takes into account information about the stabilizers of points. It's like an enhanced version of the usual cohomology that captures the stacky nature of the orbifold curve. They use this enriched cohomology to define a charge lattice and construct stability conditions with a specific central charge that interacts with the Serre functor in a really controlled way. And that's how they get the bound on the global dimension.
That's really cool how they bring together all these different ideas to get such an elegant result. It really shows the power of abstract math to help us understand complex objects like orbifold curves.
I completely agree. So now that we've looked at all 4 dimensions, we're starting to see a bigger picture. Orbifold curves, even though they're non-commutative, are actually pretty simple and coherent when you look at them through these dimensional lenses. What are your main takeaways so far?
I think what's most striking is how often we see simplicity.
Hmm.
All 4 dimensions, Rouquier, diagonal, under certain conditions, Serre, and global, are often one for orbifold curves. It seems like there's a deep consistency and uniformity to their structure. It's like we're looking at something that seems chaotic at first, but when you look closer, you see this hidden order and elegance.
I like that. It's like these abstract concepts are revealing hidden patterns and showing us the true beauty of these seemingly complex objects.
I'm wondering, do you think this simplicity is just a thing with orbifold curves, or could it be something we see in other non-commutative spaces too? Could looking at these dimensions in other contexts give us more surprising results?
It's a great question. It's possible that orbifold curves have some special features, like their connection to classical geometry and their relatively well-behaved singularities that contribute to this simplicity. If we look at these dimensions in the context of more wild, non-commutative spaces, we might see some interesting contrasts, and that could help us better understand the connection between geometry and category theory.
I'm also really intrigued by how these different dimensions interact. We saw that diagonal dimension can be different from the others depending on the canonical bundle degree. And we saw how those specific stability conditions affected the global dimension. Do you think there are even deeper connections between these dimensions that we haven't found yet?
Definitely. We've just started to explore these dimensions and their relationships. If we keep digging, we might uncover new symmetries, dualities, and insights into the structure of non-commutative spaces.
It seems like our deep dive has given us more questions than answers, but they're the kind of questions that make you want to keep exploring. It's like we've been given these powerful tools and a whole uncharted territory to discover.
I couldn't agree more. That's what makes math so exciting. The journey never really ends. There's always something new to uncover.
So let's wrap up our deep dive into the dimensions of non-commutative curves. I want to thank you for being such a great guide through this fascinating topic.
It was my pleasure. And thanks to all our listeners for joining us on this mathematical adventure.
As we wrap up our deep dive, I keep thinking about all the connections we found. We've looked at these kind of abstract dimensions, Rouquier, diagonal, Serre, and global. And they've given us such an interesting way to see these non-commutative curves.
Yeah.
What stands out most to you from what we've talked about?
I think the thing that surprised me the most is just how much simplicity we've seen. For orbifold curves, all four dimensions are often just one, especially when you have conditions like negative canonical bundle degree. It seems like there's this deep underlying coherence in these categories, a kind of hidden order that's not obvious at first.
Right. It's like all these different ways of looking at dimension are pointing us to the same basic truth about orbifold curves. And it's such a cool example of how these abstract mathematical tools can help us see patterns and the elegance of things that seem really complicated at first.
Totally. And it makes you wonder, is this simplicity just something special about orbifold curves, or is it something bigger that we might find in other non-commutative spaces? Could exploring these dimensions in other contexts lead to more surprises?
Yeah, that's a great question. I'm also still thinking about that unexpected behavior of diagonal dimension, how it changes based on the degree of the canonical bundle. It really shows how the geometry of the underlying space can affect these abstract categorical dimensions in subtle ways.
It's a good reminder that even when we're dealing with really abstract math, we can't completely ignore our geometric intuition. These dimensions bridge the gap between geometry and category theory, and they let us see how those two worlds interact.
We've also seen all these connections between the different dimensions, like how building those specific stability conditions affected global dimension, and how diagonal dimension is linked to tilting bundles and their endomorphism algebras.
It feels like we're just scratching the surface of a bigger, more unified theory. If we keep exploring these connections, we might find new symmetries, dualities, and ways of understanding the structure of non-commutative spaces.
Definitely feels like we've uncovered more questions than answers, but they're the kind of questions that make you want to keep learning. It's like we've got this amazing toolkit and a whole new world to explore.
I couldn't agree more. That's what's so great about math. It's a constant journey of discovery.
So to all our listeners, I encourage you to take a look at the source material and the papers we've cited. Really dive into the proofs, think about the results, and let your curiosity lead the way. There's so much to discover in the world of non-commutative curves.
Who knows what new connections and patterns are out there waiting to be found? Maybe one of you will make the next big breakthrough in understanding these fascinating mathematical objects.
And with that thought, we'll wrap up our deep dive into the dimensions of non-commutative curves. A huge thank you to our expert for guiding us through this amazing topic.
It was my pleasure. And to all our listeners, keep exploring the world of math. It's full of wonder and excitement.
Welcome back, everybody. Today, we're going to be taking a deep dive into the dimension theory of non-commutative curves.
Yeah, that's right. We'll be specifically unpacking the groundbreaking research of Bhaduri, Goldberg, and Robotis from Cornell and USC.
Okay.
They've been exploring how to measure dimension in the abstract realm of non-commutative algebraic geometry, focusing on a fascinating class of objects called orbifold curves.
So we've got a stack of papers from them,
Excellent.
all dealing with different ways to quantify dimension for these non-commutative curves.
And what's really cool is they don't just settle for one definition of dimension.
Right.
They actually explore four distinct notions: Rouquier dimension, diagonal dimension, Serre dimension, and global dimension.
Whoa, right.
Each one offers a unique lens through which to view the size and complexity of these mathematical objects.
So why orbifold curves? What makes them the focal point of this deep dive?
Well, there's a powerful classification theorem that essentially tells us orbifold curves, along with representations of quivers, basically define the landscape of non-commutative curves. So by understanding these specific objects, we gain insights into a vast swath of non-commutative geometry.
Okay, so before we jump into their findings, let's set the stage.
Sure.
Even I need a refresher on some of these dimensions.
Of course.
Let's start with Rouquier dimension.
Okay.
What does it actually capture about a category?
Imagine you have a set of building blocks.
Okay.
And you want to construct any object in your category. The Rouquier dimension tells you the minimum number of steps it takes to build any object, starting from a single generator object. A lower Rouquier dimension means the category is, in a sense, easier to construct.
So it's like a measure of how efficiently you can build things in the category.
Precisely.
Okay.
Now, diagonal dimension takes a different approach.
Okay.
It focuses on a special object in the category called the diagonal.
All right.
This object represents the identity of the category.
Okay.
And the diagonal dimension measures how easily you can construct this diagonal using combinations of simpler objects.
Got it. And what about Serre dimension? That one always sounded a bit mysterious to me.
Serre dimension is inspired by the Serre functor, a powerful tool in algebraic geometry.
Okay.
Think of it as a way to twist objects in a category. The Serre dimension measures the growth rate of an object as you repeatedly apply the Serre functor to it.
Okay.
It tells you how much complexity is added with each twist.
So it's kind of like measuring how expansive the category is under these twists.
Exactly.
Okay.
Finally, we have global dimension.
Right.
This one delves into the world of stability conditions, which assign a kind of energy level to objects in the category.
Okay.
Stable objects are those with the lowest energy levels. The global dimension measures the spread of these energy levels across all the stable objects.
Okay, so a lower global dimension would mean the energy levels are more clustered together.
Precisely.
All right, now with these definitions in mind,
Yes.
let's dive into the heart of Bhaduri, Goldberg, and Robotis' research and see how these dimensions play out with orbifold curves.
Let's do it.
Sounds good.
Yeah.
So flipping open their paper,
Okay.
the first thing they do is define noncommutative curves.
Right.
It seems like they're building on a previous definition where noncommutative curves are viewed as special kinds of categories.
Yes, they're working with the definition introduced by Reiten and van Bergh,
It's okay.
where a noncommutative curve is defined as an abelian category that's x-finite, has homological dimension. One is noetherian and smooth.
Whoa, a lot of technical terms there.
Uh-huh.
Can we unpack that a bit?
Absolutely. An abelian category is essentially a collection of objects and maps between them, satisfying certain axioms that allow us to do algebra within the category.
Okay.
X-finite means there are only finitely many ways to extend objects.
Okay.
Homological dimension 1 implies a certain level of simplicity in the relationships between objects. Noetherian means the category is well behaved in terms of its sub-objects.
Okay.
And smooth ensures some nice technical properties.
So these noncommutative curves aren't just any random collection of objects and maps.
Right.
They have a lot of structure baked into them.
Exactly.
Okay. Now, why is this definition so important?
So this allows them to leverage a powerful classification theorem.
Okay.
This theorem states that any well-behaved non-commutative curve must be equivalent to either the category of representations of a quiver or the category of coherent sheaves on an orbifold curve.
Ah, that's where the orbifold curves come in.
Exactly.
So if we understand orbifold curves, we've essentially got a handle on a huge chunk of non-commutative geometry.
Precisely.
Okay.
Now, turning to the next page,
Right.
we get into the nitty-gritty of Rouquier dimension.
Okay.
Remember, this is all about how many steps it takes to build any object in a category from a single generator.
And they actually managed to prove a pretty remarkable result. The Rouquier dimension of a tame orbifold curve is always 1.
It is a beautiful result.
Yeah.
It means these orbifold curves are, in a sense, minimally complex from the perspective of Rouquier dimension. They achieved this by cleverly adapting techniques developed by Orlov,
Right.
who previously demonstrated a similar result for smooth projective curves.
Let's dive into their proof.
Okay.
It looks like they construct a special object, denoted H,
Yes.
which is a combination of line bundles and generating sheaves.
Yes. This H is carefully crafted to generate the entire derived category of coherent sheaves on the orbifold curve in just one step.
Right.
They show that you can obtain any object in the category by taking cones of maps between shifts of this H.
I see. They also mentioned tame orbifold curves.
Right.
What's the significance of that term?
So it's a technical condition related to the characteristic of the base field.
Okay.
Essentially, a tame orbifold curve has stabilizer groups whose orders are co-prime to the characteristic.
Okay.
This tameness assumption is needed for certain results to hold, but it's a fairly mild restriction.
So for most practical purposes, we can assume our orbifold curves are tame.
Exactly.
Okay, now let's turn to page 3, where they tackle diagonal dimension.
Okay.
And this is where things get even more interesting, right?
Absolutely.
Okay.
Unlike Rouquier dimension, diagonal dimension doesn't always give a simple answer for orbifold curves. In fact, they show that the diagonal dimension can be either 1 or 2, depending on a subtle property of the orbifold curve.
This property is related to the degree of the canonical bundle, if I'm not mistaken.
Yes, you are correct.
Can you remind me what the canonical bundle is?
Of course.
Okay.
It's a line bundle associated with the orbifold curve, and its degree essentially measures its intrinsic curvature.
Okay.
For smooth curves, the degree of the canonical bundle is directly related to the genus, telling us how twisted the curve is.
Okay, so Bhaduri, Goldberg, and Robotis show that if the degree of the canonical bundle is negative, the diagonal dimension of the orbifold curve is 1.
That's right.
But if it's 0 or positive, the diagonal dimension jumps to 2.
It's pretty...
Yeah. What's the intuition behind this jump in dimension?
It boils down to the existence of tilting bundles.
Okay.
These are special collections of objects that can tilt the derived category, transforming it into an equivalent category with different properties.
Okay.
Orbifold curves with negative canonical bundle degree have tilting bundles whose endomorphism algebras are hereditary, meaning they have a simpler structure. This indirectly leads to a lower diagonal dimension.
So the more negative the curvature,
yes,
the simpler the structure.
Precisely.
And the lower the diagonal dimension. That's a pretty neat connection.
Indeed.
Okay, now on page 4, they delve into the calculation of Serre dimension.
Right.
As we mentioned earlier, this dimension measures the growth rate of an object under the action of the Serre functor.
Yes. And just like with smooth projective varieties, the Serre dimension of an orbifold curve turns out to be equal to its dimension, which in this case is always 1.
They use a similar approach to their Ruckier dimension calculation, right?
Yeah.
Exploiting the fact that the Serre functor essentially shifts objects by a fixed amount.
That's right.
Okay, let's move on to page 5, where they tackle the world of stability conditions and global dimension.
Yes, this is where things get a bit more technical.
All right.
To compute the global dimension, we first need to establish that stability conditions even exist for orbifold curves.
Right.
To do this, they restrict their attention to orbifold curves defined over the complex numbers.
Why the restriction to complex numbers?
It simplifies the construction of stability conditions.
Okay.
They use a specific definition of the charge lattice that relies on working over the complex numbers.
Okay.
However, they do suggest that the construction could potentially be extended to other settings using the numerical Grothendieck group.
Okay, so working over the complex numbers.
Yes.
They construct a family of stability conditions parameterized by 2 real numbers.
Oh, right.
Showing that these satisfy a key property called the support property.
Precise.
And with these stability conditions in hand, they prove that the global dimension of an orbifold curve is always 1.
Yes.
This aligns with previous findings for smooth projective curves, highlighting a certain simplicity in these objects.
Indeed.
Okay, so they've managed to compute all 4 dimensions for orbifold curves.
It's quite remarkable.
Revealing some fascinating patterns along the way.
Absolutely.
But we're not even halfway through the paper. It looks like they dive into the actual proofs next.
You're right. The real fun is just beginning.
Uh-huh. Okay.
We've laid the groundwork, but now it's time to roll up our sleeves and get into the mathematical machinery behind their results.
All right.
Are you ready for part 2 of our deep dive?
Bring it on. All right, let's jump right back into the mathematical trenches. We left off with the promise of delving into the proofs of Bhaduri, Goldberg, and Robotis' impressive results.
Indeed, their paper goes beyond simply stating theorems. It provides a robust mathematical framework to support their claims. Let's start with Theorem 3.1, which states that the Ruckier dimension of a tame orbifold curve is always 1.
This is where they construct that special object,
yes,
denoted H, right? The one that can generate the entire derived category of coherent sheaves on the orbifold curve in a single step.
That's the one. The construction of H is a testament to their ingenuity. It's not just a random object. It's carefully crafted by combining line bundles, generating sheaves, and utilizing the coarse moduli space map.
Okay.
The idea is to create an object rich enough to encapsulate the essence of the orbifold curve.
And they also utilize a lemma they proved earlier,
yes,
connecting the vanishing of cohomology groups on the orbifold curve to the vanishing of cohomology groups on its coarse moduli space.
That lemma is crucial. It acts as a bridge, allowing them to leverage the well-established results for smooth projective curves and apply them to the realm of orbifold curves.
Okay.
The proof also involves a deep dive into harder Narasimhan filtrations and the construction of exact sequences, demonstrating how any object in the category can be obtained from this cleverly constructed H.
They break down the proof into 2 separate cases, torsion sheaves and locally free sheaves.
Right, precisely. They meticulously handle each case, exploiting the unique properties of these sheaves and utilizing the structure of H to demonstrate that they can be generated in a single step. It's a beautiful example of mathematical precision and elegance.
It really highlights their mastery of non-commutative algebraic geometry.
The way.
Now let's move on to Theorem 4.6, the one that provides a complete characterization of when an orbifold curve has diagonal dimension 1.
Yes, Theorem 4.6. This one hinges on the degree of the canonical bundle.
Okay.
If the degree is negative, the diagonal dimension is 1.
Right.
However, if it's 0 or positive, the diagonal dimension jumps to 2.
Okay.
It's a fascinating dichotomy.
Can we walk through the key ideas of the proof? I know it's quite intricate.
Of course. They start by cleverly adapting a result from Olander, which states that if the diagonal dimension is 1, then the diagonal object must be a summon of a cone of vector bundles of a specific form.
And then they show that if the degree of the canonical bundle is non-negative,
yes,
this scenario leads to a contradiction, right?
Exactly. The contradiction emerges when they meticulously examine the degrees of specific line bundles involved in constructing the diagonal object.
Okay.
It's like a delicate balancing act. If the degree of the canonical bundle tips the scales in the wrong direction, the whole structure crumbles.
They also link the diagonal dimension to the existence of tilting bundles with hereditary endomorphism algebras, don't they?
Indeed. They demonstrate that an orbifold curve has diagonal dimension 1 if and only if it possesses such a tilting bundle. This connection underscores the profound interplay between geometry and algebra in this captivating realm of non-commutative curves.
It's like they're weaving together different threads of mathematics to create a rich tapestry of understanding.
Beautifully put. Their work truly illuminates the hidden structure of orbifold curves, revealing a world of unexpected connections and intricate beauty.
Now, I know we breezed through the Serre dimension and global dimension calculations earlier. Can we circle back and take a closer look at those proofs?
Absolutely. Let's start with Serre dimension.
Okay.
Recall, it measures the growth rate of an object under the repeated application of the Serre functor.
Right.
For orbifold curves, they prove that the Serre dimension is always 1, just like its dimension.
And they achieve this by utilizing a similar strategy to their Rucchier dimension calculation, right?
Precisely.
Exploiting the shifting nature of the Serre functor.
It's a testament to the power of mathematical tools and techniques that can be applied across seemingly different contexts, revealing underlying patterns and connections.
Okay, now what about global dimension? That one involves those fascinating stability conditions.
Yes, global dimension is all about the spread of energy levels amongst stable objects in a category.
Right.
To calculate it, they first had to establish the existence of stability conditions for orbifold curves, which led them to restrict their focus to orbifold curves over the complex numbers.
Can you remind me why the restriction to complex numbers was necessary?
It boiled down to the definition of the charge lattice, a key ingredient in constructing stability conditions.
Okay.
The definition they employed relied on working over the complex numbers. However, they suggested that their approach could potentially be extended to other settings using the numerical Grothendieck group.
So assuming we're working over the complex numbers,
they
go on to construct a family of stability conditions parameterized by two real numbers, right?
That's right. And these stability conditions exhibit a crucial property called the support property.
Okay.
Using these carefully constructed tools, they prove that the global dimension of an orbifold curve is remarkably always 1. This aligns with previous findings for smooth projective curves, suggesting a certain level of simplicity inherent in these objects.
It's amazing how they navigate through such intricate concepts and arrive at such elegant results.
I couldn't agree more.
It really underscores the power of abstract mathematics.
Now, flipping to the next page, we encounter the appendices, where they provide additional technical details and lemmas to support their main results.
It seems like a lot of their work involves meticulously adapting existing results for smooth projective curves to the more general setting of orbifold curves.
You're spot on. They're essentially building upon a solid foundation of knowledge and extending it to explore new and uncharted mathematical territory.
Right.
It's a common practice in mathematics. We often start with familiar concepts and then generalize them to tackle more challenging problems.
It's a testament to the power of abstraction. By working with more general objects, we gain deeper insights into the underlying principles that govern various mathematical structures.
Precisely. The beauty of abstraction lies in its ability to unify seemingly disparate areas of mathematics, revealing hidden connections and universal truths.
Now let's dive into Appendix A. They present a lemma that plays a crucial role in proving Theorem 3.1.
Okay.
The one about the Rucchier dimension of an orbifold curve.
Yes. This lemma focuses on showing that a specific object, denoted F, is a summon of a cone. It starts with an abelian category of homological dimension 1 and an object F with a subobject phi. They then assume the existence of two exact sequences that relate phi and Fi to other objects in the category.
So these exact sequences provide a sort of recipe for constructing phi and Fi from other building blocks.
Exactly. The lemma then asserts that F can be obtained as a piece of a larger object, specifically a cone constructed from maps between the objects appearing in those exact sequences. It's like they're piecing together F from the information contained in those exact sequences.
I see. They also use the fact that the homological dimension of the category is 1.
Right.
Why is that assumption important?
It guarantees that the injective resolutions they work with are relatively short, simplifying the proof considerably.
Okay.
They also use a diagram to illustrate the relationships between the objects and maps involved, which can be incredibly helpful in navigating complex mathematical arguments.
Visual aids can make a world of difference. It's like they're providing a roadmap.
Indeed.
Guiding us through the intricacies of the proof.
It makes the abstract more concrete and helps us grasp the underlying logic.
Okay, let's move on to Appendix B, which seems to focus on some technical lemmas related to stability.
Yes, these lemmas delve into the properties of Harder-Narasimhan filtrations, which provide a way to decompose vector bundles into semi-stable pieces.
Okay.
They show that dualizing a vector bundle preserves its Harder-Narasimhan filtration, but flips the slopes of the pieces.
So it's like taking the filtration, tuning it upside down, and reversing the stability order of the pieces.
Precisely. This seemingly simple result plays a crucial role in proving Part B of Lemma 3.7, which is a key ingredient in their Rouquier dimension calculation.
It's amazing how these seemingly disparate pieces of mathematics fit together to form a coherent and elegant whole.
It truly is. Their work is a testament to the beauty and interconnectedness of abstract mathematics.
We've covered a lot of ground, but there's still so much to explore. I'm ready to dive into Part 3 and see where this journey takes us.
Let's embark on the final leg of our deep dive.
Welcome back to our final exploration of dimension in non-commutative curves. It's been quite a journey, hasn't it?
Indeed, we've delved deep into the intricate world of orbifold curves, exploring 4 distinct ways to measure their dimension. Bhaduri, Goldberg, and Robotis have truly given us a remarkable framework for understanding these fascinating mathematical objects.
We've explored the definitions, walked through the proofs, and even peeked into the technical appendices. Now, I'm curious about the bigger picture. What are the lasting implications of their work? What does it tell us about the nature of dimension itself in this abstract realm?
Their research highlights a fundamental truth about non-commutative geometry. Dimension isn't a simple one-size-fits-all concept. We have multiple lenses through which to view the size and complexity of these objects, and each lens offers a unique perspective.
It's like we've been given a toolbox filled with different instruments for measuring dimension, each suited to a specific task.
Precisely, some dimensions like Rouquier and Serre dimension give us clean, elegant answers reflecting a certain simplicity in the structure of orbifold curves. Others like diagonal and global dimension are more sensitive to subtle features like curvature and the existence of tilting bundles.
This suggests that the geometry of non-commutative curves is deeply intertwined with their algebraic structure.
Absolutely, and that connection is a recurring theme throughout their work. Think back to the link between diagonal dimension 1 and the existence of tilting bundles with hereditary endomorphism algebras. It's a striking example of how seemingly disparate areas of mathematics converge in this abstract world.
They also leave us with some intriguing questions for future exploration, pushing us to think beyond the dimensions they've defined.
Yes, their work isn't just about providing answers, it's about igniting further inquiry. They challenge us to imagine new ways of quantifying the size of categories, hinting at the possibility of undiscovered dimensions that could reveal even deeper secrets of non-commutative geometry.
It's a call to embrace the unknown, to venture beyond the familiar and seek new mathematical horizons.
Precisely, and that's the essence of mathematical discovery, constantly questioning, exploring, and pushing the boundaries of our understanding.
So for our listeners who might be feeling a bit overwhelmed by the technical details, what's the key takeaway message?
The beauty of mathematics lies not just in its rigor and precision, but also in its ability to illuminate hidden patterns and connections that might otherwise remain invisible.
And in the realm of non-commutative geometry, these patterns and connections are particularly profound and often unexpected.
Exactly. By exploring different notions of dimension, we're essentially shining a light into the abstract depths of this world, revealing its intricate structure and uncovering its hidden beauty.
It's a journey that requires patience, curiosity, and a willingness to embrace abstraction.
But the rewards are well worth the effort in these abstractions. We often find profound insights that reshape our understanding of the mathematical universe.
Well, I think we've done a thorough job of unpacking this fascinating research. I feel like I've gained a whole new appreciation for the nuances of non-commutative geometry.
It's been a pleasure exploring these ideas with you. And remember, this is just the beginning. There's so much more to discover in this rich and ever-evolving field.
So to all our fellow math enthusiasts out there, keep asking questions, keep pushing the boundaries, and keep diving deep into the abstract. Who knows what mathematical treasures you might unearth?
Until next time, keep those mathematical minds sharp, and may your explorations be filled with wonder and discovery.